Right-hand rule, another step. They oftentimes talk about right-hand rule 1, right-hand rule 2. Right-hand rule 1 is very simple. It's just a case of determining which way is your current going to go. Let's say this current is going up on this wire. All I'd have to do is imagine grabbing this wire with my hand with the thumb pointing up. If I do, my hand tells me that the field would be going in on this side and come out on that side. And I could do that the whole length of the thing, and going out from it, I could say all on this side versus all on that side. But anyway, the field's going around it this way. Now on this other one over here, let's say the current's going down instead. If that's the case, right-hand rule 1 says, grab the wire thumb down. If you do, now your fingers go into the board on that side and come back out over here. So on this one, just the opposite. So in this case, the circular field going around is going to be coming out and going back in or behind over there. This, on the other hand, is going to be coming out on this side and going back in behind there. So now we know the direction of the fields, that they go around the wires, this one this way, this one that way. Now something else that happens when you do have current going through these two long wires next to each other is there's a force felt between them. That involves the other version of right-hand rule, which we've started setting up right here. Now let's take a look at this. What is the equation work that we run into when we look at this? For free charges, the force, which is the force we're talking about here, is equal to Q V cross B. Above these two.
Yeah.
Put it in.
Yeah.
Yeah, the one that we'll be dealing with for this setup looks a little different than this because you're talking about a current carrying wire. So the force that you would feel now is going to be I L cross B. Two equations that look somewhat different, but actually they're basically the same thing. And to show that, what's I? I is current. That's charge flow per time, like coulombs per second. So I can change this to an amount of charge, that's a Q, over an amount of time. And leave this as an L cross B. Now, actually, when we're talking about this, we're talking about individual charges of some value. It's a constant. So we really don't need to talk about change in charge. We can think in terms of just an amount of charge. And what's actually happening is those charges are traveling a distance L per time. So really what we're talking about is delta L over delta T cross B. What's L divided by time? What's a distance divided by time? A distance divided by time is a velocity. So all you're really saying is your charged particles are traveling a velocity through a magnetic field. And if you can see my little vectors, that is no different than that.